right? Here they're asking which of the following quantities does not have units. This is our equation. So you can conclude directly, right? N is just a number, so it doesn't have any units. But if we consider all other parameters, lambda is wavelength, so we measure it from meters, and d is also a kind of length, so we measure it from meters, and theta, right, theta is an angle, so we measure it from degrees or radians, right, degrees or radians, right. So the answer is n right here. In the second question, right, here they have given a graph of current versus potential difference of a diode, and they're asking which of the following statement is correct for this diode. First one, the diode does not conduct in reverse direction. This is wrong. You can clearly see over here we have a very small amount of current. We call it leakage current, right? So it conduct, right, in reverse direction, but very small amount of current, right? The resistance of this diode in the reverse direction is infinite. That is also wrong. Why? If it is infinite, we can't have this leakage current. We shouldn't have this leakage current, right? If you're having a current, that means, right, it is not infinite. The resistance is not infinite. The see, the resistance of the diode decreases when the potential difference is above 0.7 volts, right? Here's the 0.7, right? And if we want to calculate what resistance of this position, right, and resistance of this position, what should we do, right? We need to get, right, we need to get, let's call this one I1 and this one I2, and this is V1 and this is V2, right? If we want to calculate what resistance of these 2 points, we need to take V equals IR, right? You know Ohm's law, V equals IR, and our R is equal to V over I. It is not about rate of change, right? So don't get confused this one with the gradient. Yes, we are taking gradient at that point, at this point, right? Or you can easily tell it, easily understand it, we are taking just V over I ratio at that point. So the resistance over here is what? V1 over I1. Here what? V2 over I2, right? Then you can conclude what? I2 is over here, I2 is larger than I1, right? I2 is larger than I1. Here we have big difference between these two, and we have a difference between even V1 and V2, but this delta V is smaller than delta I, than the change we have over here I with I. So we can directly conclude what I2 is greater, right? I2 is greater, so the resistance here will be less than let's call it R2, it is R1, than R1, right? Resistance R2 will be less than R1, right? So the resistance of this diode decreases when the potential difference is above 0.7 volts. That is correct. That is the correct answer, right? This diode does not conduct when the potential difference is below 0.7. That is also wrong, because you can clearly see here we have a small current over there, right? That is also wrong, right? So you can conclude the answer by just looking at the incorrect answers, or you can conclude it by this way. You should keep in your mind what the resistance is not about rate of change of voltage. We don't have I over here, right? Or it is not about any change, it is just the ratio of V over I at that point, right? It is just the ratio V over I at that point, right? Then I2, right, the change in I2 is larger than I1, and we will have a voltage change, but it is negligible compared to I mean it is too small than the change in I, so we don't need to worry about V over here, right? We don't need to worry about V over here. We are just considering I, then I2 is larger than I1, so we can conclude what? R2 is less than R1. Or you can directly memorize this one. Even if it is a straight line, you will get what? a greater your resistance will decrease even if it is a straight line, right? Don't get confused with it. Keep that in your mind, right? Here in the third one, which of the following would increase the detail in an ultrasound scan, right? In the first one they say increasing the duration of the pulses. Okay, right, don't misunderstand this one. Right here they are telling increasing the duration of the pulses. So what is it, the meaning, what is the meaning of duration of the pulses? It is not about, right, if we have two pulses like this, right, if we have two pulses like this, it is not the time gap between them, right? We can't change it. It depends on the material that we are trying to go through with our ultrasound, right? We cannot change it. So what they have mean over here, right, here is the time duration of a pulse, right? This is what they have explained over here by this time duration, right? So they are telling increasing the duration of the pulse would increase the detail. Will it? Right? Okay, suppose we have two boundaries over here. Now we are sending larger duration pulses with larger durations, right? So what will happen, right? We are sending two pulses like this, then when they reflected back, like over here, if they have larger duration, right at this point they will superpose, right? They will superpose, and we cannot get an idea about the boundary. So if we have sent a small pulse, right, like this, a small pulse like this, they don't superpose, right? They will give the exact gap between these two boundaries, or you can tell it like this, that will increase your details about the ultrasound scan. So, right, this point or the statement is incorrect. Why? If you increase this duration, what happen, right? It will make your pulses superpose, so you won't get good details, right? Your details will be lost because they superpose. If you have sent what, a small pulses, they will give you better details about the ultrasound scan. So what should conclude from this one? Our duration of the pulses, which means time or the duration of the pulses, should be small to have a better ultrasound scanning, or it will increase the details. In the part B, increasing the frequency of the ultrasound, right? V equals F lambda, right? I hope you remember this equation. We cannot change, right? It is constant. Ultrasound, they have a constant speed, right? So if you increase frequency, what happen? The lambda, which we call wavelength, will decrease. If you can decrease the wavelength, you can get better ultrasound scanning. It will increase the details, right? Keep that in your mind. If you can decrease this one, you will get better understand or better ultrasound scanning, because it will diffract through even smaller gaps. I hope you remember when we have an electron microscope, what we are doing here is we are by using electrons, what we are doing here is we are making our wavelength smaller, so the light cannot diffract through this one, but the wavelength of the electrons can diffract through this one, because wavelength of electron is less than wavelength of light. So that's how we get better image by using electron microscopes, because they have less wavelength, right, or smaller wavelength, right? You should keep in your mind what, if we can decrease the wavelength, the size of the wavelength, you will get better ultrasound scan, right? So increasing the frequency will lead to decreasing the wavelength. So that is the answer, increasing the frequency. And if you check third one, increase the intensity, no, it has no effect, right? You should keep in your mind, if you increase the intensity of the ultrasound, then it will cause to bigger amplitude, right? Bigger amplitude, like no, it's not right, it's like this, bigger amplitude, right? So it has no effect on the details. So increasing wavelength will get you what? A less details. That's why I told you wavelength should be smaller. So if you increase it, you will get less details. So this is also incorrect, right? Answer is B. Okay. Fourth one, in a current carrying copper wire, the drift velocity of the electrons is very small. Which of the following best explains this? Right. I hope you remember what drift velocity equation. It is I over n a e, right? What is n? N is the number of charge carriers per unit volume, right? Here they say the charge of an electron is very small. So if you can make it smaller, what will happen to our velocity? It will increase. But in the question, they say drift velocity of the electrons is very small, right? Drift velocity of the electrons is very small, right? So that is not our answer. Cross sectional area of the wire is very small. So if you make it smaller, this one, what will happen to our drift velocity? It will increase because they are inversely proportional, right? The third point, the current in the wire is very large. If the current in the wire is very large, the drift velocity also will increase. Why? They are directly proportional. So the answer should be D. Let's check it. The number of electrons per unit volume for copper is very large. Yes, if you increase this one, what will happen? Right, sorry, if you increase this one, not decrease, right? If you increase this one, the drift velocity will decrease, right? So the answer is fourth one, right? The graph shows how displacement varies with time for a particular point as a wave passes. We have a displacement over here and the time over here. Which of the following statements is not correct? They are asking about the inaccurate statement. Here they say the time period can be determined directly from the graph. Yes, that is true. Why? Time period is the time taken for a complete oscillation. So if you can take time from here to here, you will get time period. B, the wavelength can be determined directly from the graph. No, that is wrong. Why? You can't find or you can't determine wavelength from displacement versus time graph, right? We'll be able to get frequency and time period, but not not wavelength. Why? To get wavelength, you need what? Displacement versus distance graph, because if you measure the distance between these two adjacent peaks, right, it will give you a measurement of length, and we measure wavelength from meters, so it should be a length. Even if you calculate the length between these two, it will give you a time, not a length, right? So the wavelength can be determined directly from the graph is incorrect, so it is the incorrect one. And wave could be longitudinal, it is correct. The wave could be transverse, it is also correct. It has no effect, right? Okay, sixth one, the length of the string Vy 0.6 meters, right? Which of the following is wavelength of the standing wave? Right, if the total length is 0.6, right, from here to here is 0.6, right, we have three loops, so if you divide 0.6 meters from 3, you will get the length of one loop, right? So if you can multiply it from 2, what you will get? You will get the length of 2 loops. So that is what we call wavelength, right? To get the wavelength, you have to divide from 3 and multiply from 2. So if you have done it, you will get the answer as B, 0.4. Right. In the next one, they're asking which of the following sections of the string would be in phase with each other. Right. That is also kind of good question. Right. Right. In this case, right, if you assume the particles of the loop VW, if they are moving downward, right, because this is a standing wave, right, they are moving like this, and the loop next to it, the particles on the loop next to it will move into the opposite direction like this, so they are in out of phase. So what happened for the particles in next loop, they will move right into direction opposite to the previous, this one, right, so they will move like this. Then you can conclude what particles in the VW loop and particles in the XY loop, they are moving to the same direction, so they are in phase, right, they are in phase. So the answer is C. Right, if you have any questions regarding this and any question that I'm discussing here, I have put my Telegram link in the description of this video. You can ask any question regarding this discussion. Right, in the eighth one, a string is placed under tension T, a wave travels along the string, a second string has the same mass but twice the length. A wave travels along the string with the same velocity as the wave in the first string. Right, you should keep in your mind what the same velocity, and it has same mass but twice the length. Right, they're asking what is the tension in the second string. So what is the equation that we should use for this one? It is V equals T over mu, right, square root of T over mu, and mu is mass per unit length. So if this is the mass, this is our L, right, it is mu over mass over length, right, it is mass per unit length. Right, then in the second one, if I write the equation for second one, they say it is same, right, the velocity is same, right, the velocity is same, so it is B. And we don't know tension, right, we don't know tension. I'm going to put it as just new tension Tn, right, and they have mentioned what it has the same mass but twice the length, so new mu, right, let's call it n in the second wire, right, it has the same mass but twice the length. So if we can write our new mass per unit length like this, right, it is 1 over 2 times m over L. M over L means mass per unit length, it is mu. So our new mass per unit length is mu over 2, right, so it is mu over 2 square root, right. So if you simplify this one, here I came to here, then I'm adding it over here, right, V is equal to 2 times Tn over mu, right. To balance these two equation, look at here, to balance these two equation, right, mu is there, we have no problem with the mu mass per unit length, and we have no problem with the velocity, right. Then this 2 Tn should be equal to T to make it balance, then our Tn should be T over 2, right. If you are familiar with this type of questions, you don't need to do all these calculations. The reason is I'm doing it because you can have a better understanding about this type of question, so you can easily conclude by looking at the question. The answer is C, right. Right, in the next one, here the diagram shows some of the energy levels for a hydrogen atom, right. Here they have given the energy, and they're asking which of the following expressions equal to the lowest frequency of the light possible from a transition between these energy levels. The first thing we have to do here, we need to find what is the lowest energy transition, right. Between these two, it is 1.36 times 10 to the power minus 19, right? If we calculate this one, it is minus, it is right here, minus 2.42 times 10 to the power minus 19 joules minus negative, right, 5.42 10 to the power stuff, right, here 19 joules. So here we have two minus sign, then this one will become positive, so it is 5.42 times 10 to the power minus 19 joules minus 2.42 times 10 to the power minus 19. So if you simplify this one, right, you will get 3.0 times 10 to the power minus 19 joules. You have to do the same thing for to take the gap between these two energy levels. Then it is minus 1.36 times 10 to the power minus 19 joules minus negative 2.42 and 10 to the power times 10 to the power minus 19 joules. So if you take it 2.4 times 10 to the power minus 19, because it will become positive, we have two negative signs over there, minus 1.36 times 10 to the power minus 19 joules, right? If you simplify this one, you will get 1.06 or something. I can't remember it properly. We'll see. Let me check it with my calculator. Right, where is it? Yes, it is 1.06, right? It is 1.06, right? Now we know what is the lowest possible energy transition. It is between these two energy levels. That is the lowest possible energy transition. So if an electron is moving right here from, if an electron is moving from here to here, or if an electron is moving here to here, right, if it is moving from here to here, they have to absorb a photon, right? But here they have mentioned which of the following expression is equal to the lowest frequency of light possible from a transition between these energy levels, right? They have to absorb a photon, and if they are moving from here to here, from top to bottom, they have to emit a photon, right? What is the equation for that one? It is equal to E equals HF, right? Here they are absorbing a photon and here they are emitting a photon. Then it is equal to E equals HF. Then what is E? E is the energy of this transition, and we have taken it. What is it? It is 2 point, here I'm going to highlight it, 2.42 times 10 to the power minus 19. So that is the energy. So if you want to take the frequency will be that change in energy over what? Planck's constant. So that is this whole thing over Planck's constant, and you can directly conclude what? The answer is D. It's over here. You don't need to even do this one. If you can conclude what? This is the minimum possible energy transition. Just look at the answers. 2.42 times 10 to the power minus 19 is over there, minus 1.3. That is the only answer which contains this whole thing, right? So you can easily conclude what answer is this one without looking at other options, right? Right, this is a kind of very beautiful question, right? Here we have two photographs, X and Y, were taken from the same car windscreen. Photograph Y was taken through a polarizing filter, right? Okay, how can we conclude the answer of this question? I know it's kind of confusing, but don't worry. Here we have a glare from this picture, right? We have a glare, right? We don't have any glare. We have, right, I know we are, if you see it in our practical lives, we see some glare, but just for the sake of argument, we can see inside the car, right? We can see inside the car. Just take that point, we can see inside the car. And why we see glare from here, right? If we have, this is the light from sun, and we have it like an unpolarized light, the light from sun is unpolarized. So here is it, and it is coming from the sun, and it will hit this what windscreen, and a fraction of that light will come towards our eye. This is what we call reflected light, and the other fraction will go through the windscreen and hit this object and come back, right? This is what we call refracted, right? But we can't see inside the car, which means this summation of the reflection and refracted light, refracted light will make this glare, so we cannot see inside the car, right? In the second picture, right, we have the same light, the unpolarized one, unpolarized light here, right? Sorry about my drawings, right? And here it will come like this, and here is our reflected one, and here is our refracted one, right? This is refracted, and this is what we call reflected, right? And we have a polarizing filter, right? You can see inside the car, right? It means the refracted light can pass through this polarizing filter, right? But here the glare is no more, right? Here the glare is no more, which means the reflected light has cut off by this polarizing filter. How is it possible, right? Though if you assume that, right, if you assume that the transmission axis of this polarizing filter, right, is this, right? This is the transmission axis, and if refracted light can pass through this polarizing filter, it should contain what? Unpolarized light. It should contain unpolarized light, so they can come like this, right? Then the reflected light, they can't pass. Why? The light should be plane polarized. That's why they can't come from this polarizing filter, right? Refracted light can pass through this polarizing filter. That's why we can see inside the car, right? The light goes through this windscreen, come back to our eyes by hitting these barriers. Then we can see inside the car why the refracted light can pass through this polarizing filter. So this is what we call refracted light, right? If they can pass through this polarizing filter, they are unpolarized, right? Unpolarized. If they cannot, the reflected light, if they cannot pass through this polarizing filter, they are plane polarized. That's why they can't pass through this polarizing filter. They are blocked from this one. That's why we don't see any glare, and that's why we can see inside the car. So the reflected one is plane polarized and refracted one is unpolarized, right? So here they don't mention the refracted, they have mentioned it like transmitted, so it is unpolarized. This is correct, and this one is plane polarized, reflected one. So the answer is C.